let's go to start with Santiago Núñez. Wait a minute. Okay, here. With Santiago presentation, the first is the research focuses. The research that Santiago is focused on understanding the complex multiscale stochastic system where thermodynamic irreversibility drives iteration across a wide range of temporal scale by means of the stochastic methods and agent-based modeling. Informatics. He studied at Universidad of Illinois in Urbana-Champaign, a bachelor at the Universidad de Costa Rica in engineering, computer engineering, and the Costa Rica Institute of Technology. The awards is SIG, I don't have the name, SIG HPCICM, Intel Computation and Data Science Fellowship in 2017, Early Career RDA USA Fellowship in 2019, in Hindenburg Laureate Forum Scholar in 2020. The presentation of Santiago is the Renormalization group theory and scheduler dependence in agent-based models to model aspect toward higher modeling fidelity. I'll leave with Santiago.
Mario, thank you so much. And I'm going to share the screen. Let me know if it's available. Okay.
It's okay.
Okay, thank you. So basically, this talk is about trying to understand the effect of scale and complexity on contagion processes, specifically those implemented on agent-based models. This work includes many collaborators and includes two pieces of work that I'm going to detail slowly. First, the motivation is, how do we know if our simulations resemble reality? We want to generate simulations in which both the predictions or the retrodictions, that is the reconstruction events, are able to tell us something about what happened or about what might happen with certain accuracy. Can we know that to begin with? Or what does it even mean to speak about what we may call model fidelity? Why does it matter? So basically, let's start by why it matters. First, we want to produce new empirically correct science, especially whenever we intersect with the social sciences, this becomes more challenging. The other part is refining existing research towards greater understanding. We want to extend what we know so that we may use it in new situations. This has been really pressing in the case of computational epidemiology in the last couple of years. Also, we want to inform decision makers in critical situations, and that can only be achieved properly if we have models that resemble reality as closely as possible. Finally, we want those models to become a component in anticipatory systems. One of the things that COVID has shown us, I believe, is that we need to have some sort of mechanism, not only to reactively attend to crises, but to prevent them in the first place. So this is called fidelity to social processes or to natural processes. So it means that agents adequately reify real entities. We have good representations. The modes of interactions of agents closely resemble those in the real system. We don't have bogus or strenuous interactions. The environment representation has the core elements that impact the real entities, and the laws that drive the simulation are in a good approximation corresponding to those of the real system. The other thing is that we want simulation states across time trajectory to correspond to the trajectories in the real systems. It is not just about the isomorphism, the approximate isomorphism between states and any given specific time. We want that isomorphism, albeit approximate, to remain consistent across multiple system states. And fidelity is defined simultaneously at the conceptual, performative, formal, computational, and informational level. So this is one of the areas of research that motivates my work here at the University of Illinois. So there are many factors that impede fidelity. One of them is limited system observability. Maybe we can't see everything that's happening. Maybe there's irreducible complexity. that we don't know about. There's an inadequate choice of observables and metrics, an inadequate abstraction of problem features, or maybe inadequate assumptions about the computational substrate. So we are going to focus on today, and of course, inadequate computational implementation of the ABM frameworks. And we are going to focus today on a bit of the choice of observables and metrics and the computational implementation of ABM frameworks. So let's go directly to the examples. The first case study, this is work that was performed with my late advisor, Professor Eric Jacobson, in 2020 here for the community of Urbana, Illinois. I'm going to be rather quick about it. And it is about using renormalization group theory, which is a technique in statistical physics, specifically of very useful in condensed matter physics and in solid state physics, to understand how we can simplify a system while preserving some of the core properties. So what we started with, the core setting of the problem is this. We were in between May and July of 2020. The university had closed and there were plans to reopen the university. So the big question was, can we do so safely? And the way to do that was to start looking at the natural trends. Of course, there's detailed data. And the way Illinois worked was by having at the decision-making level a series of indicators that if they were on the green, things would be good. If they were not on the green, it means that things would have to be descaled to a phase in which there were more constraints, more mobility constraints, more isolation constraints. And there were 6 main of those. However, we wanted to focus on our community. So the University of Illinois is the university is those 2 zip codes. There's some city around, and the rest is a rural area, mostly cornfields in a place that is mostly flat. But most of the population is concentrated on those 2 zip codes that are roughly 15 square kilometers. So one of the things that happens is when the university is in full swing, when it is in full semester in spring and fall, the population in these 2 zip codes goes up to 132,000. However, when people leave for summer vacation, for summer holidays, there's only 100,000. So there's a differential there, and there's a migration process after summer going into fall, and that was what was anticipated. So the question was, what happens in 2020 when a bunch of people who might carry a higher viral load than that in the community come into the university? How does that impact the university first? So the university had a very comprehensive system for testing, for tracing, and a lot of actions. And this is Professor Nigel Goldenfeld here in physics, who was in charge of a lot of the strategy. But this strategy only comprised students and faculty. It did not comprise the whole of the community, because that was out of the scope of the responsibilities of the university. So there was an app that this app prevented or allowed access to buildings. If you were positive, if your COVID test came positive, then you could not access the building. Otherwise, you had a free entry in this sense. Now, it is important to note that all the population of the university, the 55,000 people, were tested 2 times a week. Everybody, and it was a saliva-based test, and the data coming out of those tests was available 6 hours after the test was performed. I won't go into the biotechnology behind this, but it's quite fascinating. So from March, when the first case was detected, up to August 19th, here's where the concerning period was going to happen, because from August 19 and ahead is when most of the students are going into their dorm rooms, are being allocated into their facilities. And that's when a lot of people would come with, or we expected them to come with, a higher viral load than the one present already in the community. This is data from the Champaign-Urbana Public Health District Department, and they have been very generous in terms of making the data publicly accessible and available. So we started calibrating, and we started looking at the trends and said, well, can we start by calibrating at April 9th? And there were a bunch of measures. For example, mask wearing happened very early on in May. Also, the lockdown started fairly early on in March 28th. So we started around April 9th to do the calibration process. So we calibrated the model, and we started by building a simple extension of the SIR model. So we have susceptibles, there's a probability of contagion. Those become symptomatic and asymptomatic with a Bernoulli probability of being asymptomatic and a Poisson probability of remaining in the same place. We're going to talk about that later. Then there's a probability of becoming severe, and there's another probability depending on sex and age of becoming deceased. And there was a Poisson probability of being recovered. Now, we operated on testing strategies and contention strategies in the susceptible, exposed, symptomatic, and asymptomatic levels. So I won't go into the details of the model because of time. I want to concentrate on the technique. So roughly, we assume that there are n agents. The number of agents don't change through the course of the simulation except when you introduce new agents. There's a percentage of those that have been exposed at the beginning, and there are other events. So people traveling through the community that may be infected, they just leave, but they propagate the disease. So they generate new outbreaks. They have a probability for inbound rate of infections. And also you have the ability of a percentage or a proportion of the existing agents, which are going to be new agents. This was to simulate the influx of students coming into the community. So you get a larger pool of agents, and then some of those go into isolation. Okay, so the main problem was that when you have one agent infecting one agent, the probability of contagion works in a direct manner. However, the way the simulation was written with the tools that we wrote it using Python meant that we could not scale beyond 2,000 agents and still have runtimes below 1 hour. That was a requirement when we started talking to the mayors of both cities. They said, we want to have a tool that allows us to run these scenarios in less than 1 hour, because we need to make decisions on the spot really quickly, and that must be preserved. So the question was, how can we rescale the probability so that we obtain the same results, but with a fewer number of agents representing a larger number of people? And one way to do it that we looked at was renormalization group theory, which is basically we have a system that can be described by some measure of action, a Hamiltonian or another functional. And we find that there's a physical critical point, there's a state of interest. And we want to know, even if we rescale quantities, if we change the parameters of this Hamiltonian or this functional, whether we can still preserve approximately the same trajectory up to a certain point where the system diverges and we can no longer recover it. But the important point is, can we simplify the computation by using this, by making this trajectory or by changing properties of the system without changing the properties of the critical point? So what kind of renormalization group we looked for? It had to be time independent. The average effective reproductive number is the remaining quantity, the fixed quantity, and the value of n should change with respect to decimating agent population by a factor of r. So we started by saying, okay, let's suppose that the probability of contagion for a given agent can be stated parametrically in terms of the number of agents. What happens if we have a rescaling factor? For example, R100 means one agent equals 100 people in real life. And because we are looking at a system that can be understood as an interacting particle system, hence guided by Boltzmann statistics, we created this answer, which seems reasonable. And hence we are going to be looking for a function alpha that describes, according to R and gamma, which become the critical exponents of the system, how the reduction can be performed. So we said, okay, again, Boltzmann statistics, G equals E, and then alpha, this should be natural logarithm. So alpha, the function is the natural logarithm of a function called beta of R and gamma. So the simplest choice we could find for beta, of course, was logarithm in base gamma of R. And after some manipulation, we get this simple expression, 1 over log gamma R Pn. And this gives us a number Kr. Kr is the rescaling factor depending on R. Now, finding gamma is the real challenge. That has to be done empirically, and that has to be done in tandem with the other assumptions of the system. So to gain the assumptions, we started with a rectangle, well, square grid or rectangular grid. Every point had what we call a dwell time. It means agents spend, every time an agent spends here corresponds to 15 minutes in reality. 15 minutes for the original strain of COVID is the minimum time that it takes for someone to become infected, if they remain at the same place. So this is a toroidal geometry. Agents move across the torus. And then we took into account the size of the grid, the number of agents, and we calibrated that against population densities and against different types of mobility. In the community, we have good mobility data that allowed us to do that. That's important. I will repeat every once and then in this presentation. In this specific work, we could only do it because we had sufficient data. And then the effective reproductive number should be proportional to population density, and it is more an indicator. It was not the main quantity of interest, and it was not really relevant for the prediction that happened later. But it was a good way of seeing whether the simulation happened correctly. And here, this is the average number of interactions between susceptibles and infected people that led to actual infections. So the public policy measures that we implemented, they had a beginning time and an end time, and we had a probability of contagion that was decreased depending on the efficiency of the self-containment. For example, if you were asking for food and an Uber driver came and was infected and you did not take sufficient precautions, that may be one occasion in which people got infected. Mask wearing and social distancing, we were able to generate a couple of those. And also, we also implemented in the simulation contact tracing. To model the effect of gases or the effect of droplet dispersion, we used recent research by Boruba in 2020 that studied how how the distribution of emissions of particles, of droplets, happen in different situations, and we were able to come up with an expression for that, which is an exponential decay model. The other thing that we did was, okay, decision makers wanted us to deliver a model that could be run within 1 hour, and to do that, we found that R had to be equal to 100. That led to a specific value of gamma with the simulation data that we had and the calibration process. And if we rescale too much, if R is very large, if every agent is equal to 10,000 people, then we get a white noise distribution. This is well known from the theory of renormalization. We get a point in which the fixed point has no certain, it becomes indistinguishable with noise. If we full run one agent per person, a single run would have been 23 hours. So basically, we found that still with one agent representing 100 people, we got a very good approximation that was feasible within 1 hour. So it was a 23 times performance gain. This is important when designing simulations. You want a simulation that runs quickly. And also, we also wanted to run an ensemble with many cores, many compute cores. So the question is, how many cores do I need so that the interval of confidence of using one core and one more core is reduced? It means, how can I reduce the size of the confidence intervals by increasing the size of the ensemble? And we found that with 30 cores, we got below 0.05 change in the width of the confidence interval, and this was good enough for decision makers. So that's how we made the choice of processors. Finally, we did with 25% testing, with 50% testing, 75, and with a counterfactual with no testing. This eerily resembled what happened in North Carolina, because they didn't have testing, they didn't have proper measures. We also did strong confinement. We also had policy-based confinement. The city asked, what happens if we close establishments? What happens if we close bars, if we close places where students often go? And also, what happens if there are delays in testing? And finally, we use this one in combination with the university data. And this is the final peak that was between August 18, 2020 and September 7, 2020. And this is our model. So quite a good fit, frankly. And we are still understanding some of the implications. We have there's a publication in the midst being written at this point, but it seems that the modeling technique did have a quite close resemblance with reality. So what we learned, we can use RGT in ABM models that are isomorphic to interacting particle systems. They can have significant input in execution times and sample sizes. These advances are possible due to an ideal situation here where the data and proactive testing existed, but more complex models introduce memory effects, and renormalization group is harder to obtain or maybe not feasible at all analytically. So this was the first lesson, and in the time that I am left, which I think it's about 9 minutes, I'm going to show a bit of another piece of research connecting through. So basically, in some situations, RGT allows us to preserve model fidelity, that is the closeness to reality, because it has a form that mathematically conforms to an interacting particle system. And then we don't run into complications while looking for the critical exponents. Again, this is not always the case. So the second case study we then looked at the framework, at the software running these things. This was presented last year, the computational social science in a reduced form. And what we tried to study was this. Whenever you run an agent-based model, there's a piece of software, the ABM, and it has a piece called the scheduler that sorts events. There can be a global ordering, you can do local orderings, or you can randomize things in a fully random manner in a staggered way, so only certain things are randomized, or you can write specialized randomization software. So there are cases where ordering of events matter. If you're voting and the voting process is public, or who votes first matters, or even if it is secret, depending on which populations vote first, things matter. Negotiation with partial information, games, and socially wicked problems are situations in which having the right order matters. So we asked, can we find a simpler system where we can introduce complexity in a controlled manner? And the answer is yes, a simple contagion model coupled with social action. So we have the traditional SIR model. We are going to be only looking in the following graphs, not in this one, at infected, recovered, and deceased. And we overimposed a small world network, Watt-Strogatz network. So the idea is agents that are in the social network will try to copy the behavior of their peers. Agents that are not connected in the social network are unlikely to copy the behavior of their peers. So if most of my social networks decides to move, then I move. If most of my social network decides to stay, then I stay. This is mimicking isolation, self-isolation protocols in the presence of social network and social pressures. We also had an odd number of agents in the network for majority reasons. And then the scheduling is driven by priorities based on network centrality. We had to generate a criteria or generate criteria for determining these priorities. So basically, these are time ticks. There's one step in the simulation. This is another step. And then we have multiple agents. So what we do is look at their social network. Some agents have a greater degree of centrality. They have many more nodes going in. They have a higher in degree and out degree. Some of those are much less significant. So these green ones are the first ones to be going to be marked. These yellow ones are other ones that have less centrality. And probably these red ones are ones in the edges, right? Some agents that are leaf nodes in this graph. So basically, higher centrality, medium centrality, and lower centrality. And then this is a complete time step. So there's randomization among these, but there's sequentiality, and this represents hierarchy, the impact of hierarchy on these systems. We did a design of experiments in which we have two schedulers, the priority random that I described, or the random. We have two population sizes, and we have social mimicry that can be selectively turned on or off. My apologies, this should be on in here. And whenever social mimicry is on, we have a series of parameters like the degree and beta for the Watt-Strogatz network, death after infection, the agent step size, if an agent can take just one step in the grid or can take multiple steps in the grid, and also mobility, whether all agents move the same distances or agents move across different distances. So let's look at the results. Result one, when we first wanted to see that when we introduced a new type of scheduler, that we could reproduce the same results as with the traditional random scheduler. And yes, Qualitatively, we were able to reproduce the same behavior, so we did not introduce any additional concerns. And this is with an ensemble of size 30. That's why we have the shaded regions. Second result is that varying parameters in the social network appears to accelerate simulation time when using the priority random scheduler. So some of the features that we observed here in very early on could be translated earlier in time. That means some events happened earlier in the simulation with a higher degree than with a lower degree. And this seems to be consistent. Okay, result number 3, increasing the mean degree results in fluctuations when the prioritized random scheduler is used for sufficiently long times. So in this case, we see that there's an increase in a slight decrease in the changes in concavity of the function. That seemed interesting. That is going to appear more evidently later. And then when we densify the Erdos range random network, this results in a shorter simulation time altogether with more fluctuations for heterogeneous agents. This means that agents that move across the grid with very different step sizes take much shorter to reach a terminal state in the simulation. This is really important because this means that one can understand this as the result of a mean field approximation, in which if the correlation length in a mean field approximation is longer, the system will take a shorter time to look everywhere the same. So the other thing is that a sparser and more regular random network results in longer simulation times with less fluctuations for heterogeneous agents. And this is interesting in the sense that when we do the faceting of the system, one of the difficult things to study this system was how do we facet it in a way that is informative. So in this case, we have 2 schedulers, different steps, homogeneous and heterogeneous. And what this says is basically the more regular the network, the more it looks, the more time it takes. Why? Because then again, mean field theory argument, we have places where distances are relatively the same, they may be shorter. Hence, for everything to look the same, it takes a longer time. So information takes a longer time to propagate, even if there's a social network attached. And the result number 6 is the parameter beta. If we look at beta, at a low beta, there is oscillations in this system, in this part. However, if we look at beta in the case of the purely random model, it works as a dampening force. And this has been observed before in what's called resonant fluctuations in epidemic models. We finally did something, which is we classified using C 5.0 to just reveal with the results that we have how the simulation space can be classified. And finally, what we found is that the models with heterogeneous agents that move across at different speeds across the grid, have a richer structure than those that don't have it, that are more homogeneous. So what do we learn in the minute that I have? That scheduler differences matter in the long-term behavior, that they are modulated by social behavior parameters, that systems with homogeneous agents appear to be less sensitive to these scheduler differences, and that the effect of the models clearly work with 1,000 agents. So there's a critical size of the system that matters. That dynamics appear to be compressed when agents are heterogeneous, and we find resonant fluctuations in stochastic disease models, and those are relevant for decision making. Are we really erasing fluctuations? Are those outbreaks? So finally, for the conclusion slide, and I won't take more than probably 30 more seconds, doing agent-based modeling requires challenging the assumptions about computational tools and methods rigorously. We cannot blindly use them without doing so. The other part is that renormalization group theory in tandem with the statistical mechanics inspired models provides an empirically tunable avenue to balance fidelity and compute time, and this is critical for the methods. Coupled spatial social and contagion simulations are simple enough to understand via statistical mechanics and can be made complex enough, just complex enough to interrogate and ask interesting questions. And this requires parsimonious and careful design of experiments. And this means we don't always need big data or machine learning, but those have to be deployed very specifically in very well controlled situations where you have to prove that they are needed, and only then. So open questions, more work is needed around compressibility of ABM models, especially when they are more complex than the traditional contagion model. Deeper sampling of the parameter space is required for the contagion social model, and using ABMs for decision-making implies transparency about choices, assumptions, and limitations, and this is critical for decision-making support. Thank you so much. I am open for questions.
Thank you, Santiago. Any question, comments? Questions.
También, si gustan, podemos hacer las preguntas en español o como gusten. Me indican nada más.
Parece que no tenemos preguntas. No hay preguntas, no questions. Bueno, no sé, Santiago, si algún comentario final. Pues.
Sí, tal vez para una de las cuestiones que nos tomó algún tiempo implementar y que es parte de lo que estamos en proceso de documentar para publicación es teoría de renormalización. Es el lograr encontrar este tipo de reducciones de dimensionalidad, uno podría considerarlos, porque al fin y al cabo el proceso de decimación es reducir dimensionalidad en un espacio muy complicado. Es una serie de técnicas que requieren más atención y que vale la pena estudiar matemáticamente también a profundidad, porque no solo por la utilidad, sino que tienen, por ejemplo, hacen referencia a funciones holonómicas a veces, también a cuestiones de homogeneidad, tiene que ver también con suposiciones de continuidad, y hay mucho que es un área muy fructífera de investigación, entonces creo que vale la pena poder echarle una ojeada a estos métodos de una manera más rigurosa. En este caso, para el caso del modelo, encontrar ese grupo de renormalización fue muy afortunado, que terminó en una función muy sencilla, pero nosotros luego hicimos este mismo ejercicio para un modelo para este mismo modelo que tiene la mímica de comportamiento social, y no logramos llegar a una expresión única. Encontramos serias dificultades a la hora de determinar, de encontrar una forma cerrada que solamente se refiera a exponentes críticos del sistema en una forma parecida a esta. Entonces, creo que eso es algo que me gustaría anotar, y luego, en el otro caso, como un modelo sencillo, bastante sencillo un modelo sencillo de agentes, puede generar comportamiento que es bastante diverso. Estamos en este momento haciendo muchos más experimentos con una mayor densidad del barrido paramétrico para tratar de generar algo más cuantitativo y no solamente preliminarmente cuantitativo.
Una pregunta, ¿qué tanta potencia de computación, qué tanto equipo computacional necesitan para manejar esto? Porque...
Ajá, esa es una muy buena pregunta. En el caso del modelo de COVID que nosotros corrimos para Illinois, lo hicimos con Amazon Web Services, porque aquí para ese momento, entre julio y diciembre del año 2020, todas las supercomputadoras fueron reservadas por diferentes organismos como el NIH.
Todo el mundo estaba.
Correcto, estaban corriendo modelos, pero eran modelos de la biofísica del virus. Entonces no tuvimos mucho acceso. Lo que hicimos fue con un pequeño grant de Amazon Web Services, tener una instancia que tenía 36 núcleos, 64 gigas de RAM. Y debido a que logramos hacer esa renormalización de que cada agente equivaliera a 100 personas, fue que logramos llevar cada simulación debajo de 1 hora y que llevamos a que el consumo de memoria fuera suficientemente bajo.
Okay. Sí, sí,
Entonces,
todo eso es parte. De hecho, ahora que hablas de dimensión, eso es parte de estadística que trabajamos nosotros también, pero nada más en otro nivel, ¿verdad? Tratar de bajar la dimensionalidad para tratar de tratar el mismo problema, pero con menos datos. No sé si
exactamente.
tiene algún otro comentario, pregunta, any question, comments.